Hello everyone and welcome to Robot Operating System version 2 or ROS2 Jazzy Jalisco tutorials. In this ROS2 Jazzy tutorial, we explain the basics of the ROS2 control framework or the ROS2 control library, and we explain how to simulate robots and controllers in the Gazebo simulation environment that you can see over here. The ROS2 control library contains a number of useful packages for real-time control of robotic systems. The ROS2 control library enables us to simplify the integration of new hardware such as sensors and actuators and deployment of control algorithms. This library implements a number of standard controllers such as PID controller for set point tracking, position controller, velocity controllers, trajectory controllers, differential drive controllers, and similar control algorithms. On the other hand, the Gazebo simulation environment is one of the most popular simulation environments for robotics and investigation and performance evaluation of ROS2 control algorithms. Before we start with explanations, here is a brief demonstration of what you will learn in this video tutorial. Over here, we have modeled a robotic system consisting of two links. This red rectangle represents the first link and this blue rectangle represents the second link. There is a joint between these two links. The joint is a rotational joint. Although this is a relatively simple robotic system and the geometry is significantly simplified, everything explained in this video tutorial applies to more complex and to more realistic robotic systems. In this terminal, we can send control commands. That is, we can control the position of this joint. We do that by using a single line. Here it is. And over here, that is here, we specify the angle of rotation in radians. So let's go back to plus 1.2 radians, and if I press this, you can see how the robot moves. And you can see obviously that dynamics is modeled and robot control actions are relatively smooth. So what's happening behind the scenes? First of all, we have a complete dynamics model of these two links. That is, we have modeled the mass, moment of inertia, geometry, etc. On top of that, we have implemented a ROS2 control plugin which implements a simple feed-forward controller that controls the position. You can also implement feedback controllers, you can implement model predictive controllers, etc. Here for demonstration, it's very important to keep in mind that we have keep this simulation as simple as possible, not to blur the main ideas with too many ROS2 modeling details. As you will see later on, the code is already complex. For example, here is the code or a piece of code that models the robot geometry and inertia properties, as well as the control parameters. Then you have several addition files, such as this file that models Gazebo parameters, as well as this file over here, parameters.xacro, that completely parameterize the model geometry. Then on top of that, you have this controller file that defines the control parameters. You can see that this is a feed forward or forward controller. And then on top of that, you have this display.launch file that brings up everything. That is, this file starts all the nodes and makes sure that Gazebo is properly configured. On top of that, you have the package and CMake files. All these files will be explained in detail in this video tutorial. That is, we were going to implement a ROS2 package from scratch that implements the controller and Gazebo simulation. On top of that, we have created a manual that thoroughly explains all the steps that you need to perform in order to implement this model and this exercise. And here's the manual. The manual is 8-page long. Links to this manual, as well as to all the files explained in this video tutorial, will be provided in the description below this video tutorial. Before we start with formal explanations, let's first summarize what is explained in this video tutorial. In this tutorial, we explain, number 1, how to implement a minimal example and a ROS2 package that demonstrates how to use the main functionality of ROS2 control library from scratch. Number 2, how to properly write URDF, YAML, and other files that define the ROS2 control parameters. Number 3, how to define and implement the Gazebo plugin and interface for the ROS2 control framework. And number 4, how to simulate the motion of a robot controlled by using the ROS2 control framework. For simulation, we use both RViz and Gazebo. In order not to blur the main ideas with too many details in this tutorial, we are using the simplest possible example of a robot and a simple ROS2 control implementation. The main idea is to teach students how to properly build the package and all the configuration files. Everything explained in this tutorial can easily be generalized to more complex examples and more complex ROS2 controllers. Here is the license and the copyright notice. This document, develop code files, lesson video, and all the provided material are referred to as the learning material in the sequel. Number 1. The learning material is the ownership and the original work of Dr. Alexander Haber, who is referred to as the author in the sequel. Number 2. You have the right to use the learning material for personal educational use and strictly for non-commercial use. Number 3. The learning material should not be copied, redistributed, or publicly posted on public or private websites, code repositories, and social media platforms. Number 4. The learning material should not be reproduced manually or automatically using an algorithm or an AI model from this video and then posted on public or private online repositories. Number 5. Unless allowed by the author, the learning material should not be used as lecture material on online learning platforms and in university courses. Number 6. Unless allowed by the author, the learning material should not be used to organize courses for training engineers working in companies or paid academic researchers, such as paid students, paid postdocs, paid professors, etc. Number 7. The provided code files and learning material should not be used to train an AI algorithm or a large language model. And number 8. Unless allowed by the author, the learning material should not be used to produce academic papers, student reports, or other documents. Okay, so let's start with the prerequisites. To implement the material presented in this tutorial, you need to have Linux Ubuntu 24.04. Do not use Windows Subsystem for Linux or WSL since you might have issues displaying graphics. Install Linux Ubuntu on your computer. If you have a Windows computer, then you can install Linux Ubuntu in parallel to the Windows operating system by using a dual boot approach. Let's verify that you have the proper version of Linux Ubuntu. To do that, click here, open a terminal, and over here in the terminal you need to write only a single command. Namely, you need to write this command. And this command will list your Ubuntu version. As you can see over here, I'm having Ubuntu 24.04, and this last number 2 really doesn't matter. Okay, the next step is to verify that you have the proper version of ROS2 installed on your system. You need to have ROS2 Jazzy Jalisco. To verify that ROS2 Jazzy Jalisco is installed, type this command, and this command should list the content of the standard installation folder, which is given over here, or better to say its path is given over here. And if ROS2 Jazzy is installed, then this folder will most likely be non-empty. That is, you will see these files. However, this is not complete verification. To completely verify, we need to first of all execute the standard setup.bash file that will set up the ROS2 environment, and then we need to print this ROS environment variable, which will tell you what is your current ROS2 distribution. It's Jazzy in my case. However, that's still not the correct verification. The best verification is to try to build the package, and we will do it later on. However, if these steps do not produce an error, then most likely everything is fine. Next step is to install the necessary ROS2 and Gazebo packages and verify that they are installed. In this tutorial, we will need several ROS2 packages. Some of these packages are the standard part of the ROS2 desktop version. First, we will need the Robot State Publisher package for the Robot State Publisher node. This package receives the joint state information and by using the robot model calculates the poses of every link and sends the information to the TF topic. We will also need the RViz package for simulating the robot motion. This package is used to visualize the geometry and motion of a robot by using a simple graphics user interface. Then we will need the Xacro package in order to parameterize the robot model and create macros. Next, we will need the ROS2 control and ROS2 controller packages that implement the ROS2 control framework. Finally, we will need to install a package for integrating the ROS2 control framework with Gazebo simulation environment. And finally, or better to say firstly, we will have to install Gazebo on your system. So first of all, make sure that you update and upgrade everything by running this command, and then enter your password, and over here be patient. It's going to take a while to execute everything. Press Y over here and wait. Patience is a virtue. You always need to have patience when playing with ROS. Then again, source the environment by executing this command. And then let's start with installation of packages. First of all, we need the robot state publisher. Then we need the RViz package. Then we need the Xacro package. Note over here that all of these packages are already installed on my system. This is because I have installed or tried to install these packages in the past. Then we need the ROS2 control package. Also, I installed the Xacro package. Let me just repeat this just to follow everything. Then control we installed. Then we need the controllers. Then we need these two packages that will actually install the plugins for using ROS2 control in Gazebo environment. So install this and then install this package. Okay, and that's it. The next step is to install Gazebo Harmonic. This is the recommended version of Gazebo for ROS2 Jazzy. To do that, we need to execute this command. So this command will do the following. We'll actually install Gazebo for your current ROS distribution. So this segment over here will return Jazzy. So press enter over here, and in your case you'll see that actually Gazebo will be installed, and it's going to take a while since Gazebo is, I think, 500 or 600 megabytes. So you have to be patient. In my case, Gazebo is already installed, and consequently you see only this. Next, we need once more to source the environment, and don't forget to do this after you install Gazebo, because if you don't do that, you will not be able to run Gazebo. And after you do that, make sure that system can find the default Gazebo folder. Here it is. And then let's start Gazebo just as a test and see if it works by running this command. And let's try to run, for example, one of these test examples. Here it is. And then click here to start this example, and over here you can play with this humanoid robot, since this is an integrated simulation in Gazebo. Okay, good. Now you can safely close Gazebo and we can continue further. Now we are all set. A good approach to verify that the package is installed is to run this command. Now, if you run this command, you're going to list all the packages on your system, and you can search for the packages we just installed. However, this list is really large. However, there is an easier way to search for a package. You can simply run this command. This command will call ROS2 package list, and then it's going to filter the result, and it's going to search for all the packages that contain the word control in their name. And if you press enter, you'll see all these packages. So let's do the same thing for Gazebo to see what are the Gazebo packages we have. Okay, it doesn't seems that we don't have. However, I think this is the GZ is actually the abbreviation, and you can see all these Gazebo packages. Good, good. The next step is to create the package, URDF, YML, and Python launch files. So let's learn how to do that. Okay, let's now close this terminal and let's start from scratch. I suggest to everyone to do things like this. Okay, click here and search for terminal. And over here, I'm going to resize the terminal such that you can see what I'm typing, and also you can see the commands over here. Remember, every time you want to build a ROS2 package, you need to source the environment by running this command. Then go to the home folder, and in the home folder, let's create two folders. The first folder is control_workspace. This is our main workspace folder, and inside of that, we are creating the source folder. Okay, the source folder will contain the source files of our package. Let's navigate to the source folder. And then inside of the source folder, let's create an empty package. To do that, we need to execute this command. The name of the command is ROS2 package create. Then you need to specify the build type, which is CMake. That is, we are using CMake to build the package. CMake is the build system for C++, for Python and other languages. And over here, we need to give a name to our package. The name is demo control. Press enter. And now if you type this command, you'll see the package folder. So let's navigate to this package folder. And inside, several folders and files are created. First of all, we have cmakelist.txt and package.xml. These are the configuration files of our package that we will edit later on. And then we have include and source. Include and source folders are the folders that contain or that can contain source files. In this video tutorial, we are not going to populate include and source folder. Instead, we are going to create several additional folders. These folders are going to contain the files for implementing the model. And to create these folders, we need to run this command. This command will create launch, model, and config folders, and press enter. And let's see what is being created. Here they are. Let's explain what are these folders. First of all, the config folder will contain files defining the configuration of our viz simulation and defining the configuration of our controller. Then the launch folder will contain the Python file, or better to say the Python launch file, that will start all the nodes and that will configure everything. Then the model folder will contain the model files. It's going to contain three files. The first file will be the parameter file, the second file will be additional Gazebo parameter file, and the third file will be the actual file that implements the model and that includes these other files. Okay, let's continue. The next step is to create the model of the robot. First of all, let's go to the model folder. Currently it's being empty and we need to start creating files. In this video tutorial, I'm going to use Visual Studio Code, and I started Visual Studio Code by typing this. If you don't have Visual Studio Code on your system, then you can go to the YouTube channel and there is a video tutorial I created explaining how to install Visual Studio Code. To find this tutorial, simply search Visual Studio Code installed Ubuntu. Okay, so let's create the files. The first file name is parameters.xacro. So let's create that file by clicking File, New File, and let's call it as parameters.xacro. Okay, again, parameters.xacro. Here it is. Make sure that you save it in the model folder, and over here to save time, I'm simply going to paste the content of the file. First of all, let's explain the purpose of this file. This file will define the model parameters. That is, this file will define the model dimensions, the model moment of inertia, and some other properties, such as material name, or better to say, colors. But before we explain this file, let's go back and let's analyze the geometry of our robot. Our robot consists of two links. This first blue, or better to say red prismatic element is actually the first link, and the second one, the blue prismatic element, is the second link. The model is parametrized. That is, the link dimensions are parametrized by A, B, and C. These are the dimensions in the X, Y, and Z directions. Then we have this S parameters. The S parameter is the distance from the base to the center of the link, represented by this light blue or light green dot. And then we have this Q dimension. This Q dimension is the distance of this point over here. This point is the origin of the joint connecting first and the second links, and the distance is Q from the base. Okay, so we need to define these parameters. So how to do that? Well, here's how we do it. First of all, we define that this file is an XML file. Then this line represent comments, as well as this line, and this is the standard tag. This standard tag, starting with robot, is saying to the ROS system that this file contains some interesting details about our robotic system. We start the tag with robot, then we enter this link over here. This is pretty much standard, and over here we end the robot tag at the end of the file. Everything between start robot and end robot defines some geometrical properties. Over here we are going to use Xacro macros to simplify, or better to say, to parameterize the model. Here's how we define the dimensions A, B, and C. And if you go back over here, here's A, here's B, and here's C. In our case, they are 0.1, 0.1, and 0.8 respectively. Then we need to define the parameter S. Where is the parameter S? Here it is. Obviously, S is C over 2, and this is how we write it by using Xacro. And then we need to define the Q value. This is the first joint displacement in the Z-axis direction. If you go back over here, here's Q. Good. Let's continue. Then we need to define the material density. We need the material density since we need to model the moments of inertia. Here I'm assuming the density of 2700, and the value, or the better to say, the parameter or the variable is D. Then I need to define the mass. The mass is simply density times the volume. So here I have density times the volume. Volume of prismatic element is A multiplying B multiplying C. Then I need to define the moments of inertia. Here's how I do it. These are the standard formulas for the moments of inertia of a prismatic element. Namely, if I click over here, here are the formulas. This is the Ix, Iy, and Iz. That is the moments of inertia around the corresponding X, Y, and Z axis. Okay, so let's go back. This is how these formulas are implemented. Then we need to define a macro that defines a complete inertial section of the robot body. We are going to use this macro in another file. Okay, we will explain that later on. For the time being, let's define this macro. This is how we define macro by using Xacro. We start the inertial section, we end the inertial section, then we define where is the center of the frame that's located at the center of the link. Here it is at location 00S from the base. So let's go back here and see. This center over here is located at the coordinate 00S from the base, or the world coordinate system. Then the mass value is equal to m. Over here we define them, and here is the inertia. This section over here defines the inertia tensor, or better to say, the inertia matrix. We need to specify the Ix, Iy, and Iz, and then we need to specify these Ixy, Ixz, and Iyz components of the matrix of inertia. Matrix of inertia is symmetric, and consequently we only need to define 6 entries, and that's it. And over here we need to define the additional color macros, or the color shortcuts. Here's the code for the blue color. Here you can see RGBA color code. R stands for red, G stands for green, B stands for blue, and A is the transparency. And if you want to model blue, then you will write 001, since B should be 1, and transparency here is 1, meaning that the element is completely non-transparent. And we do the same thing for the red color. Okay, and here's the first file. Simple as that. Let's save this file and let's continue further. Next, we need to define an additional file that implements the Gazebo plugins. Okay, so let's learn how to do that. Click on File, new file, and call the file as gazebo.xacro. Make sure that you save this file in the same folder and click on create file, and over here paste the file content. So let's save this file. First of all, we need to again specify that this is an XML file. Then we need to start the robot tag and we need to end the robot tag. And here comes a very important part. Here we need to specify the ROS2 control plugin for Gazebo. So we start the Gazebo tag and we end the Gazebo tag, or actually we start the Gazebo tag, we end the Gazebo tag, and over here we need to start the plugin tag and we end the plugin tag. Let me just rearrange this such that it's nicely written. Okay, it is now. So let's see. What is the plugin file name? Here it is. It's Gazebo 2 ROS control system, and here's the name, Gazebo ROS2 control, and here's the plugin name. And over here we need to define additional parameters. So what are these parameters? Well, here we need to pass to this file parameters of our controller. The parameters of our controller will actually be placed in the configuration folder. That is over here. And the name of the file will be robot_controller.yml. Note over here that we still didn't create that file. Now let me explain you one additional thing. So what is this thing over here? Find demo control. Well, this is a shortcut, or better to say a command, that will retrieve the path to your package folder. So what is the package folder? The package folder is actually this folder. Okay, here it is. Or actually, no, I have to be precise. I have to be more precise. The package folder is actually this folder. Okay, so correction, the package folder is this folder, and we can simply find the shortcut, or no, sorry, not again, I have to correct myself, not the shortcut. We can find the path to that folder by simply typing find and demo control, and this will retrieve the absolute path of this folder over here. And then we need to specify the relative path. Our configuration file will be inside of the configuration folder, and the name of the file is robot_controller.yml, and that's it. Next, in order to be able to simulate in Gazebo our model, we need to define some additional properties. For the first link over here, we need to define mu1 and mu2 parameters. These are actually the friction parameters, and we need to do the same thing for the second link. Note over here that first link and second link are still not defined. They will be defined in additional file. We are going to explain that file in the sequel. And over here we are specifying colors for modeling and visualizing the model in Gazebo. We have the red color and we have the blue color, and that's it. Simple as that. Let's save this file and let's continue further. Finally, we need to implement the third file. This third file is going to include this file, and it's going to define the robot geometry. Click on File, a new file, and call the file as model.xacro or Xacro. So it's model.xacro, and press enter, save it in the same folder, and here is the content of the file. Let's save this file and let's continue. Now, one very important thing to keep in mind is to always check the names. The name should be model.xacro, and let me double check that the name is correct since I wrote this file previously. So it is model.xacro. So it's correct. Let's explain this file. First of all, we need to specify that this is the XML file. Then here we need to specify the robot tag, and note over here that compared to the previous files, that is compared to the parameters and gazebo.xacro, over here we are specifying the robot name. The robot name is simple robot, and this part over here is standard. And over here comes the magic. Here we include additional files inside of this file. First of all, we include the parameters.xacro file, and then we include the gazebo.xacro file, and this is how we do it. And keep in mind this modeling strategy. Here, we separated the implementation into 3 files. In this way, we have significantly improved the readability and structure of our project. Namely, if someone wants to look into the parameters, he will simply go to the parameters file and he will change something. If a person wants to play with a plugin or with some other Gazebo properties, he will look in the gazebo.xacro file. And this improves the readability of our code. And then over here we need to define links and joins. First of all, over here I'm defining a dummy link which I called the world. In Gazebo and RV simulation, this world over here will actually be a coordinate system. Then I need to define the first or dummy joint, which will be a fixed joint. This is how I do it. Then I need to specify the parent link, it is world, and I need to specify the child link, it's the first link. Note over here that we still didn't define the first link. For those of you who are not familiar with URDF modeling, I created a video tutorial explaining how to properly implement URDF files, and I explained in that video tutorial all these tags. So go over that tutorial if something is not clear in this particular tutorial. However, let me just briefly explain the main concept. Whenever you want to model a joint, you need to specify a parent link and a child link. Okay, I'm going to go back to this important definition later. So let's start defining the first link of the robot. So where is the first link? Here it is. How do we define this link? Well, we start link tag, we end the link tag, we start the visual section, we end the visual section, we start the geometry tag, we end the geometry tag, and inside we define the geometry. Our link is simple box or prismatic element with the dimensions A, B, and C in the X, Y, and Z directions. Then we need to specify where is the center of our link with respect to the previous coordinate system. The previous coordinate system is actually the world coordinate system, which is actually attached to this fixed joint. And we can see the displacement is S. That is, it's over here. In this way, we have centered the link. Now over here we specify the color is a red. Note over here that this color is important for the RV simulation. This color is not going to affect Gazebo simulation. For Gazebo simulation, the colors are defined over here. Keep in mind these things. And that ends the visual element. Then we need to define the collision section. The collision section is important if you want to detect collisions or for motion planning. And over here we just copied the geometry section. And here comes the magic. Here we are using the previously defined macro that defines the inertia of our body. This macro is defined here in the parameters file. Consequently, when you type this, the URDF interpreter or the XML interpreter will look into the parameters.xacro and it's going to use this macro over here, and that's it. This was the first link of the robot. Next, here's the second link of the robot and the first joint. And here comes the magic and the power of URDF. You want to define the first joint. You start like this. You specify that's a revolute joint. This is the joint that connects this link and this link. Consequently, you need to specify the parent link. This is the first link. And then you need to specify the child link. This is the second link, which will be defined in the sequel. And then you need to define the displacement and rotation of the coordinate system attached to this joint. The origin of the frame attached to this joint is over here. We can see it's displaced for Q with respect to the base, and it's displaced for B in the Y direction. And consequently over here we simply type B and Q, and we don't have rotation of the coordinate frames. Next we need to specify the axis of rotation. In our case, the axis of rotation, as you can see over here, is the Y axis, and consequently over here you have 0, 1, 0, and then you need to define the effort. So what is the effort? The effort is the maximum torque that can be applied to this link. The maximum torque is 5,000 Newton meters. The velocity, or better to say the max velocity, is 10 radians per second, and over here you define the upper and lower rotational limits for our revolute or rotational joints, note over here that these angles are expressed in radians. Consequently, this number is minus pi over 2 or minus 90, and this number is pi over 2 or 90 degrees. Next, you need to define the dynamics, you need to define damping and friction, and that's it. Next, we need to define the second link. Here is the definition. The second link is the exact copy of the first link, so nothing special. The only change is the change in the material color, which is blue, and that's it. And then you need to define the inertia of that system, and here comes a very important part. Here we need to add or to define the ROS2 control plugin. Okay, first of all, we need to start the ROS2 control tag and we end the ROS2 control tag. Then we need to name the controller. I'm calling it as robot controller, and the type is system. And over here you need to specify the plugin. Since I'm using the Gazebo simulation, you need to use this plugin, very important. And over here you need to define several additional parameters related to the joint you're controlling. First of all, you need to refer to the joint you're controlling, and this joint has to be defined previously. In our case, it's defined over here. Then you need to specify what is the command interface name, such that we can control its position. Then you need to define these min and max parameters, and you end the command interface. And for the state interface name, you also give position, you end joint, and you end the ROS2 control tag, and that's it. Simple as that. Looks complex, however, it's just a pattern and a template. So save this and let's continue. Next, we need to define the controller YAML configuration file. So where do we use this file? Namely, if you go to gazebo.xacro, you can see over here that we are adding additional file. That is this configuration file. So let's create this file. First of all, copy this file name, then click on File, New File, and then let's paste this file name. Oops, I made an error. Let me see, File, New File, and then let me, oops, again, and never mind, I have to write manually. Let me press Ctrl V, no it's not. Let me do again, File, New File. Okay, so let's write it, robot underscore controller .yml. Okay, so let's save this file, go to the demo control and go to the config folder and save it over here, create file. Make sure that this file name, robot underscore controller, matches robot underscore controller over here. Okay, and let's type the content of this file. Here it is. I'm simply going to copy and paste it, and let's explain what's happening over here. You need to define two things. You need to define the properties of the controller manager, and you need to specify the type of the controller you're going to use and its properties. So let's start with the controller manager. You need to define these ROS parameters. The update rate is 10 Hertz. This means that we are sending 10 commands per second. Then you need to specify what is the joint state broadcaster. This joint state broadcaster enables us to visualize the robot motion. In reality, this can also be a feedback control or some kind of a sensor enabling you feedback control. And over here we're using the forward position controller. Consequently, we are specifying the controller parameters, or better to say the type of the controller, and over here we are specifying the configuration of forward position controller. Again, as the parameters, here comes a very important part. You need to specify the joint that you're controlling, and this joint name should precisely match the joint name in your model.xacro file. So if you go down, find the section first joint and make sure that the first joint name is exact over here. On the other hand, if you have 10 joints, you will have to specify the joint's name over here, and you need to specify the interface name. The interface name is position. Simple as that. Let's save this file and let's continue. And here comes a very important step. In this step, we need to implement the Python launch file that will start all the nodes. The name of this file should be display.launch.py. So let's create this file. Click on File, New File, and call the file as display.launch.py. display.launch.py. Okay, display.launch.py. Save it inside of the launch folder. And let's continue. Here I'm going to paste the content of the file, and I'm going to explain this file line by line. First of all, we need to import the necessary libraries and packages. We do it over here. Then we need to define the package name. Note over here that this package name should precisely match the name of the package you created. Then we need to specify the relative path of 3 files. The first file is model.xacro, the second path is config.rviz, and the third file is robotcontroller.yml. Note over here that these relative paths are defined with respect to the path of this folder, that is, of the base package folder. Okay, this function will define how nodes are started, and it will configure everything. First of all, we need to retrieve the absolute paths. To do that, we need to first of all retrieve the path of our base package folder. That is the path of this folder over here. We can simply do it by calling this line, and then we need to form the absolute paths of the Xacro, rviz, and the configuration, the controller configuration file. So let me just add the comment, okay, such that we know what we're doing. So first of all, we retrieve the absolute path to our Xacro model file. Then we retrieve the absolute path to the config rviz file. Note over here that this config rviz file, that is, this file is still not being created. We are going to create it the first time we run our rviz simulation. Then, as I mentioned previously, we get the absolute path of the rviz, and then we get the absolute path of the controller config file, and that's it. Now over here for verification and for debugging, I'm simply printing the path of the Xacro model file. Then we need to read the Xacro model file. We simply do it like this, and we store it in robot_desk, standing for description. Then I define this dictionary containing the model Xacro or URDF description. Then I'm declaring the arguments. First of all, I'm making sure that I will start everything, or that rviz will start with everything. To explain in this video tutorial, I'm going to start both rviz and Gazebo simulations. Then I need to initialize the arguments, that is, I need to run this line over here, and then over here I need to start defining the nodes and launch description and configuration. Over here I'm defining properties for starting Gazebo. What is important to note over here? Gazebo is actually the package that we installed. That is, we are not creating this package, we are including the standard package. And then over here we are searching for the path of the ROS Jazzy sim package, and then we are adding a path to the Gazebo simulate launch file. This is the standard launch file for Gazebo, and we didn't write this file. Right? This file will be called, and it will run the Gazebo simulation. Then over here we need to pass the launch arguments. These launch arguments are mainly the name of the empty.sdf file. This is the empty world file. That is, we want to place a robot at the center of the empty Gazebo world. And over here we launch the conditions, or better to say, let me correct myself, we specify additional launch conditions. Then we need this property here for headless simulation. Again, we are using this package, we are using the same file, and we are specifying headless rendering. I'm not going to go in details and explain what is this, you can search online. Then here comes a very important part. We need to define the Gazebo bridge. It's actually a node. The package is ROS Gazebo bridge. Then we need to specify the executable, we need to specify these additional parameters related to clock, and where do we want to print out on the screen. Then we need this node in order to actually start Gazebo simulation and to spawn our model. So again, we need to use this package. We need to call the executable create, output is screen, and here come the additional arguments. We need to specify the topic. This is the standard robot underscore description topic, and this is the URDF model. And by doing this, we are passing the URDF or Xacro model. And then here we're specifying additional name, and we are allowing renaming, and we're specifying true, and that's it. Here come the standard ROS2 control nodes and the ROS2 standard nodes. First of all, we need the robot state publisher node. This node will receive the joint state information, and it will solve the forward kinematics problem, and it will create all the coordinate transformations such that we can display the motion. So we need the robot state publisher as a package, executable is robot state publisher, output is screen and the terminal, and over here we need to pass the robot URDF description. Note over here that robot underscore description is precisely this parameter dictionary containing the URDF file of your robot, and that's it. Next, we need to start the RVS node. We need to define the parameters. So here comes the executable, package, name, and screen. And over here, we are passing the absolute path to the RVS configuration file, which will be created at the first launch of RVS. Then we need to specify the ROS2 control node. Here is the node that's being used to make an interface between the command line and to move everything. Here we need to call the package controller manager, executable is given over here, and we need to specify the path to the configuration file. So where is this path defined? If you go up, here it is, and here is the relative path. This is the absolute path to this file over here. Good, let's continue. We stopped over here. Then we need joint state broadcaster. Again, the principle is the same. Controller manager, spawner, and the joint state broadcaster is an argument. And then we need the forward position controller. To do that, we need again to use controller manager. We need the spawner. We need to specify forward position controller as an argument, and we need to specify the parameter file, and the parameter file is the ROS2 control parameter via AML file. That is this file over here. And then finally we group all the nodes and configurations inside of this node list, and then we simply run this line, and this will do the trick. This will return everything, and everything will be started at the same time. Okay. Not too bad, right? It looks complex, however, it is not after you spend some time understanding this file. So let's save this file, let's save this file, let's save this file, let's save this file, and let's continue further. The next step is to modify the configuration files. Namely, we need to modify package.xml and cmake list.txt files. So let's learn how to do that. To modify these files, let me now just do this. We need to do the following. First of all, let's start with the package.xml. So click on File, Open File, then go to this base folder and open package.xml. So let's open this file and let's add what needs to be modified. Over here, after this line, you need to add these lines. And let's explain what's the purpose of these lines. These lines are telling to our package management system that our created package will depend on some standard and installed ROS2 packages. And these packages are controller manager, this is the ROS2 control package, forward command controller, again ROS2 control package, robot state publisher, this is the standard ROS2 package, Xacro is the standard ROS2 package, RVS is the standard ROS2 package, and here are the additional bridge packages which enable us to bridge ROS2 and Gazebo. We need ROS Gazebo bridge, ROS Gazebo simulation, and Gazebo ROS control. Good, let's continue further. Next, we need to modify cmake list.txt file. To do that, first of all, save this file, click on File, Open File, and open cmake list.txt. Here it is. Then over here, you need to add a simple line. And here's the line. Let me now copy this. And here it is. Okay, and let's explain the purpose of these 4 lines. Here, we created 3 additional folders. We created launch, model, and configuration folder. Now, we need to tell to the CMake build system that there are files located in these folders. And we do it by simply calling install. We specify the name of directories or the folders, and we've specified the destination. Simple as that. Let's save this file and let's continue further. And we are almost done. The next step, which might be the most crucial step, is to try to build the project. To build the project, make sure that you're in the terminal where you source the based environment, or if you're not, run this command once again, then go back as I did to the control_workspace folder, that is to the base workspace folder, and inside of this folder, run this command to install ROS2. ROS2 is a very useful tool for verifying that everything installed is installed properly. Then initialize, and then update. Ignore errors if you see them, since they are not important currently. And over here, we need to run this command. This command will check if all the packages and all the dependencies are properly installed. Run this and you should get this. All required ROS2 installed successfully. And finally, we can build our package. To build our package, we need to run this command. The name of the command is build. Then we need to specify this option or parameter symlink install. Then we need to specify that we want to build a specific package, and then we specify the name of the package. Here is one very important comment. You can also just type build and all the packages will be built. However, imagine you have 1,000 packages, then 1,000 packages will be built. In this way, we are just isolating and building a single package. And in our case, build with no parameters or just by specifying the package will not make any difference, since we have only a single package. So let's run this command and let's hope that there are no errors. First good sign, no errors. The next step is to start the launch file. To start the launch file, open here a new terminal, and now be careful. Here you don't need to source or to execute the base ROS2 environment. You need to actually create an overlay. That is, you need to source or to execute setup.bash inside of the created package. That is, you need to execute this command. And now we can run this command. This command will start the display.launch.py file inside of the package demo control. And the command to start the file is ROS2 launch, and press enter. And let's see what will happen. Okay, so let's see now, are there some errors over here? So if you scroll all the way up, and if you go down, you shouldn't see any errors. Maybe warning or something like that is fine, but you shouldn't see any error. Error is usually marked in red. So let's see what happened. First of all, RViz is opened. However, we don't see any model inside of RViz, and that's perfectly fine, since we need to do several adjustments over here, and then we need to save the configuration file, and then we will be able to see the model in RViz. However, you will notice also that Gazebo is open, and here it is. Here is our model. Gazebo doesn't need additional configurations to display the model. So this is the first good sign. So let's fix the issue with RViz. To fix the issue with RViz, first click on Add, then scroll down, click on Robot Model, click OK, then over here, expand this menu, and under Description topic over here, click on Robot Description, and here it is. Okay, so here's the robot description. However, we can see that the links are not properly being oriented. To fix that, click here on Fixed Frame and click on World. and now you will see your model. And these are the adjustments that you need to make. Now let's save this configuration. To save this configuration, we still need to figure out what was the name, or to remind ourselves what was the name of the configuration file. If you go back to the python.launch file, you will see over here the file called config.rviz, and this is the file that we need to create, and this file should be stored in the config folder. So let's copy this. Let's go back to rviz, and then over here click on File, Save Config As, then go to the base workspace, then over here go to the source, go to the package folder, and then go to the config folder and save the file as config.rviz. Click on Save. Now let's do the following. Go back to the terminal where you started, or from where you started rviz and Gazebo, and press Ctrl C, and you will kill all the nodes and all the processes. Now go back to the original terminal and repeat the build command. Then go back to the launch terminal, then source the environment once again, and then start the launch file. And now you will see that link is displayed. However, it's going to take a while until the complete model is displayed. Now rviz is properly being set up, as well as Gazebo. Perfect. The next step is to learn how to obtain more information about our models and how to control this model. So let's learn how to do. First of all, let's open a new terminal by clicking here, and in this new terminal, let's source the base environment. Here, you need to source the base environment and not the setup.bash file inside of your package. Okay, and then let's first list all the control or hardware interfaces. To do that, you need to run this command, and after some time, you should see this. First of all, you should see the command interfaces, and here it is. And you should see the state interfaces. Here you should see available and claimed. This means that everything is okay. Next, let's obtain additional information. Let's obtain the information about controllers. To do that, simply execute this command, and let's see what will happen. And we can see our controller. It's a forward position controller. It's active, and we can see the joint state broadcaster, and we can see the joint state broadcaster is also active. Next, let's figure out what are the topics. To do that, simply run this command, and let's see the topics. You can see a bunch of topics. Some of these topics are actually coming from our control library, such as this topic over here, and these topics over here. And for us, the most important topic is this one. This topic is used to transmit or to send control commands. So let's learn how to send the control commands. Here, there are several approaches to do that. You can either type something like this or type something like this. In this video tutorial, I'm going to type this. However, when you copy and paste this inside of your terminal, make sure that you don't enter a new line over here, but just space. This new line is actually just from Word. It should be just space. Okay, so let's now copy this command, and let's explain what this command will do. Don't execute it immediately. Make sure that you correct everything. So make sure that this is in a single line. So what do we do over here? We're publishing by using ROS2 topic pub, and then we are using this topic, right? And then we are sending the message of the type standard message float 64 multi-array, and you can see the message over here. And finally over here you need to specify this data structure, which specify that you are sending data, and here's the value of data. Here we will move the joint to the minus 0.5 radians. So let's learn how to do that. Okay, so do this, and then let's go over here and let's see what will happen. So let me now just position this nicely. Now when I press enter, the robot should move. Let's see, will it happen? So press enter, some time happened, and the robot is moving. Beautiful. Okay, let's now do Control C. And let's try, for example, plus 1.2, and let's see what will happen. Press enter, and now the joint moves. Amazing. So this thing really works. The next step is to obtain additional information about the state of the system. To do that, let's open a new terminal over here, and inside of this new terminal, again, let's source the environment by typing this, and then in this new terminal, let's run this command. This command will echo, or it will display on the screen the joint states. And if you do this, if you press, you can see what's happening. The position is minus 1.2, and that's precisely the position that we are setting over here. And that's it. In this video tutorial, you have learned how to properly set up ROS2, how to model ROS2 in Gazebo, and how to simulate the controller in Gazebo.